Good afternoon, everyone.
Good afternoon, sir.
Okay. Share screen. Okay. Yesterday we saw isothermal transformation, which is also called as time, temperature transformation. That is TTT. Both means the same. So seeing the transformation with respect to time at constant temperature. So how the nucleation time depends upon the undercooling. We already saw that. So that this time is the nucleation time. And then you have the S curve, which is nothing but the transformation in percentage. This is 0% and this is 100%. So this is like 675 degrees Celsius. So how an austenite phase for an steel how it is getting converted from an austenite phase, that is gamma austenite, to alpha plus Fe3C at constant temperature. So you go above 900 degrees Celsius and then taking the sample to 675. That means quenching it very fast. So how it can be done so that you can have a liquid which is going to be 675, maintain that at 675 and keep the sample in that at 675 and see the transformation with respect to time. So for different temperatures, studies has been done, 625, everything up to room temperature, and you get all the different S curves. So by using the drop down method, having the same scale bar, time, seconds, and this being temperature. So if this is 727 line, 675, so this is the 0%, and this being the 100%. So like this for all the curves, it has been done, and at last you end up in a curve which is going to be like this. So this is what we saw. This is the procedure. The procedure also we saw that same sample, different samples of the same material, quench at different temperature, 675. This may be 650, 625, 600 like this, and seeing the transformation with respect to time. For sure, everything this is at 900 degrees Celsius and austenite phase. So at last you end up with this curve which is of importance to us. So why it is importance? Because what are the different phases you get at different temperature. So up to 550. Sorry. This is the nose. So around 550, this is the 550, that is the nose of the curve tip. So you get here coarse perlite, medium perlite, fine perlite. So anything you are doing before 550, you always end up some perlite structure. So at small article, that is the temperature which is going to be near 727, you end up in coarse perlite, and then as you go down, you end up in medium perlite and fine perlite structures. But the moment you go below 550 degrees Celsius, you end up in bainite. So for sure, bainite and perlite are two competitive structures. So you cannot directly convert bainite to perlite or perlite to bainite. So if you want to do anything like that, you have to go back all the way to this austenite phase, and then only you can come to anything, or vice versa. But directly from perlite to bainite or bainite to perlite, it is not possible. So that is a competitive phase between these two. So below 550, if you go, you get upper bainite and lower bainite. And then if you go below 200, and if the cooling rate is fast and you quench it to around 200, then you end up in martensite, retained austenite, all this structure comes. So this is what was done in the previous class. So coming to our main slides. So this is the TTT diagram for a eutectoid steel. When I say eutectoid steel, you already know it is 0.8 carbon percentage. Or somebody will say 0.76 carbon percentage, accepted. Both are okay. So 0.8 we will refer from now onwards. So 0.8 carbon percentage eutectoid steel is there. So if you do this TT diagram, you end up in this coarse perlite, medium perlite, fine perlite. If it is 550, and below this you end up in upper bainite and lower bainite up to temperature of 220. And if it's very fast, then you end up in martensite austen, and still faster, you end up only in martensitic phase. So the importance of this diagram, as I told yesterday, you can decide what phase you want in your material and the percentage of phase you want in the material, or you want a combination of different phase in your material. All these are possible if you know this diagram, or if you have this diagram. So if I have a material which is going to medium carbon steel, so I'll take 0.8 itself. Eutectoid steel I'm having. Now if I want only my material should be very soft and ductile, highly ductile. The strength is not an important, but the ductility is very important for that steel. Then the thing is, I will go up to 900 degrees Celsius or above 727, and I will go up to only. This is 1 second. So this is 1 second. So within 1 second, I'll drop the temperature from 727 to 675. I maintain the temperature up to 675 for a duration of time. So how much duration I'll tell now. So this is 0%. So at this point, the transformation is started. And at this point, the transformation is finished. Although at 675, the sample is at 675, but my complete transformation from austenite to coarse perlite is already done. It's only after that, it's only like cooling into room temperature. So that means from 727 immediately quench to 675 and keeping the sample for 10⁻³ seconds. The moment I do that, my sample will have only coarse perlite structure. Or else, okay, I want only upper bainite. So within 1 second, I have to drop it to some, say 500 or 525. And then at keeping the temperature constant and see, allow the transformation to occur. So the time duration is 10 seconds. So the moment I drop from 727 to 500 degrees Celsius and keep the sample for 10 seconds, my sample will convert to upper bainite structure. There may be a student who wants to have both perlite and bainite structure. So that is also possible. You can do that also. So we know that 50% conversion is the center dotted line, which already mentioned here. So this the dotted line in the center is nothing but your 50% conversion. Transformation has occurred. So this one is your 0% points which you connected, and this one is your 100% conversion. So what it can be, how it can be done. So from room temperature, you are heating to 900. Everything is in austenite, and from 727, initially you are going to drop. So say I want to have medium perlite, 50%. So 1 second, you drop it. You do the transformation till this 50% line. So that means initially, which was completely austenite, has now converted only 50%. So 50% is only converted to medium perlite, but the remaining 50% is still austenite. So this is done at a temperature around say 600 degrees Celsius, and the time duration, it's again you have to draw a straight line and then see how much seconds you are keeping it there. So maybe 5 seconds. Okay, so 5 seconds you have kept it, and then you converted into 50%. They converted 50% into medium perlite, and remaining still austenite is there. Now what you have to do is take the sample which is already converted 50%, and again you have to quench it to a temperature where is the range of bainite. So if you are going to quench it, say around 400 degrees Celsius. 400 degrees Celsius. And then if you allow it for the transformation, the remaining austenite is getting converted to bainite. So it starts with the 0th second. Sorry. Okay, 0th second it starts. And after 5 seconds, it's at this position, maybe. And after 5th second, you then do the quenching at the second at 400 degrees Celsius. For sure, this is the first transformation, and this is the second transformation. So from here, it is 0 to 5 seconds, and then from 5 to say what we can see, say some time it is there and it is changing. But the thing is, for this transformation, this is the initial 0. And for this transformation, this phi is the initial 0. That means for this transformation, again, it starts from the 0th second only. Although it is the 5th second, but it is the 0th second for the second transformation to occur. So that means again you are going it back and keeping at this 0th second here. So a dotted line. And then you are going to do the transformation. So this is 10 power 2 seconds or 100 seconds. Okay, so then 5 to 105. So that means 0 to 5 was the first one. 5 to 105 was the second one. Truly speaking, for the first one, it is 5 seconds. Again, this is from 0 to 100 seconds. So these are the two transformations which can be done to get 50% baronite and medium perlite. So how to represent in the graph? This is how it is done. So you quench it to 600, 50%. You have to go reverse because that is the second transformation and that is the initial second for the second transformation. So overall is different for each transformation. It is always in the 0th second, which is going to start. So then you quench it to 400 and then you rub it. For sure, generally it is mentioned as a straight line and then you go dotted at the back. But you can do this also, it's still fine. So then the transformation occur and you get this baronite and medium perlite. So coarse perlite, medium perlite, fine perlite, the structure is already known to you. So you have alternate grains of alpha plus Fe3C. And you have the grain boundaries. It's a hypo or hypereutectoid. Based on that, you can say whether it is proeutectoid ferrite or proeutectoid cementite. Similarly, baronite. So this perlite formation is completely based on nucleation process. Whereas the moment you go below 550, then nucleation is not of so importance, then it is diffusion process. So diffusion process take place below 550 and that is the only reason you see that this curve which is going in this direction is turning back in this direction, because after 550 it is a diffusion controlled transformation and before up to 550, from 727 to 550, it is a nucleation controlled transformation. That's the reason this curve again is increasing. For sure, at lower temperature, the diffusion is reduced. So that's the reason it again goes. So once the diffusion is getting reduced, that means you cannot get a perlite structure. You can get only finer structures because because it has to get converted to perlite, but the diffusion is very slow at lower temperature. So you get finer structures. So at higher temperature, you get less finer structures, and at lower temperature you get more finer structure because of the temperature range from 550 to 220. So that's the reason the baronite and perlite are like competitive phases. So it's very important that if you want to convert one to the other, you have to go back to the austenite phase all the way and then only do the conversion. So we already saw that. So this is the first one where we saw the conversion of an austenite phase to coarse perlite structure. So initially you have completely austenite, and this red line is your 0%. So this red line is your initial where the transformation has to start. So once it crosses this, that means the transformation has already started. This center blue line is, as I mentioned, it is the line which is giving 50% indication of the conversion. So if it is crossed this point, then it is a 50% of your phase has been converted from austenite to coarse perlite, but still 50 is still remaining. For sure, then you have 25% also. 75% also. Okay. So this is only an imaginary dotted line which gives an indication how much percentage. That's what I said. Once you have this TTT diagram, you can decide what phase you want in your material at the end material and how much percentage you want in the material. So once this is done completely and it crosses this 100% line, that is the 100% transformation line. Although the sample is around this temperature, the conversion is complete. Austenite has completed to perlite. Then there is no transformation. If transformation occur from perlite to something else, again it has to go back to austenite, and again you have to do another cooling method or another time transformation temperature. Then only you can change it. So once this is converted, although at 650 degrees Celsius, nothing further is going to be done with that. So once then you are only going to cool it to room temperature. So that is the final phase you get in the microstructure you get in your material when you do at 650 and above, below 727. So coarse perlite, fine perlite, the structural difference, as I mentioned before, it is nothing but the interlaminar distance. So if this interlaminar distance is greater, then it is coarse perlite. If you see here, they are very finer. So again here, this is medium perlite. So it's a combination of medium perlite and fine perlite structure here. So this diagram is representing 1.13 weight percentage carbon. So when it is 1.13 weight percent, it is greater than 0.8 carbon percentage. That means this is an hyper eutectoid. So for hyper eutectoid, this line comes into the picture, which gives the formation of pro-eutectoid cementite. Which gives the formation of pro-eutectoid cementite. So again, if you are before this range, no pro-eutectoid cementite is formed. But somewhere in between you go here, you have always end up in a pro-eutectoid cementite and you have an austenite. So maybe I'll do a transformation at this point and then I'll show you the structure. Already you know that, but still for few around 650 and going to do the transformation. So at this point, it is completely austenite. Again, this point completely austenite, but when it is in this range, so around the grain boundaries, we have our pro-eutectoid cementite. So pro-eutectoid Fe3C. This is still austenite. Okay, this is still austenite. And now when it is going to cross this point, so this pro-eutectoid cement will be there. And now initial formation of the perlitic structure will happen around the starting range here. So 0%, 50%, 100%. At 100% when it is converted completely, oh my God. Then you get your perlites. So if you see carefully, I have made the interlaminar distance larger, indicating it's an coarse perlite. And this one, eutectoid cementite. 3C. Similarly, this happens for carbon content less than 0.8. Same curve you can use. Only thing is here it is not going to be cementite, but it is going to be alpha prime, that is proeutectoid ferrite, if the carbon content is less than 0.8. Okay. So this is the formation of bainite transformation. Since I said it's going to be a finer distribution, so you get elongated Fe3C particles, and it is going to be an alpha matrix, alpha ferrite matrix. Okay, as mentioned, it is also an diffusion controlled transformation. So 0%, 100% conversion. Temperature below 550, up to a temperature of 220 it is possible. So when do you get upper bainite? The temperature ranges, if you are going to go with temperature between 300 to 540 degrees Celsius, you end up in upper bainite. And if you are in the range between 200 to 300 degrees Celsius, you end up in lower bainite structure. So again, here also it is mentioned. So perlite and bainite transformation are competitive. So transformation between perlite and bainite not possible without first reheating this to form austenite. So this is already mentioned. One more thing. Okay, diffusion is a slow process at low temperature. This phase has a very fine microstructure because of the slow diffusion rate. One is your one more structure. So this particular structure is possible only if you reheat your sample to 700 degrees Celsius and keep at 700 degrees Celsius for 24 hours. So annealing, you already know the process. What is annealing? So annealing of perlitic or bainitic. So any coarse perlite or medium perlite structure or bainite phase, upper bainite or lower bainite. You are not going to do the phase transformation. So you are going to keep it only below 727. So if this is 727, this is 727. So below this particular zone, so around 700 degrees Celsius. So from room temperature, you go up to 700 degrees Celsius and keeping this perlitic or bainitic phase for 24 hours. Then you get an spheroidite structure where you get cementite spherical particles, which is in alpha ferrite matrix. So all this white is alpha ferrite matrix and cementite are the particles. Why this is so? Because laminar structure we saw in perlite. So cementite is in laminar form, but here you see spherical structure. If you consider spherical structure and laminar structure, this is more stable structure. Thermodynamically, this is more stable structure. So at 700 degrees Celsius, this perlite laminar structure will get transformed into an perlitic structure, into spherical structure. So the next comes your Martin-Secret transformation. So we already saw that if you quench it very fast, and if this is the critical cooling rate, so the rate so this is the critical cooling rate, which is just passing the nose. Critical cooling rate. Yeah. Anywhere if you go faster than this cooling rate, you end up in martensite. So this martensite transformation is completely diffusion-less transformation. So a lot of stress will be there in the material because diffusion is also not allowed here, or limited diffusion is there. So you end up in, although you end up in the stage of alpha ferrite, it is not going to be an alpha ferrite structure, but it is going to be having a different crystal structure. That's the reason it is called as a martensite. So how is martensite formed? So formed from austerite when you cool it rapidly. It doesn't involve any diffusion. It is nothing but sudden reorientation of the carbon and iron atoms. So initially FCC, which is the gamma austenite, has to get converted to alpha ferrite, which is VCC, but it doesn't happen because you are doing quenching. And since quenching is done, no diffusion taking place, so only reorientation of atoms are taking place. So rather than forming a VCC structure, it is going to form an body-centered tetragonal structure. Because the carbon which has to go into the interstitial sites will not go to the interstitial site, but it is going to be in the edge of the unit cell. So that's the reason the crystal structure gets elongated and you get a body-centered tetragonal structure. One more point, martensite is an metastable structure. That means it can be there as a martensite indefinitely at room temperature, but it is going to transform to equilibrium phase if you do annealing at elevated temperature. So transform to equilibrium phase means it can get converted to tearlite or any other structure if you anneal the sample at elevated temperature, as we saw for our spheroidite structure. One more thing, it can coexist with other phase and also is a microstructure in Fe3 system. It is a non-equilibrium, so that's the reason it is not in the iron carbon phase diagram. Moreover, it is a non-equilibrium phase. So gamma austenite, which is FCC, getting converted to VCC. Happening, if you see the structure, this is how it is. So the carbon atom generally is in the interstitial sites. So if you take an cube, so what are the interstitial sites? You already know, right? So iron atoms will be there in the lattice points. So if you see this interstitial sites, they will be in the center point. Again, octahedral site. So this point edges I'll connect. So this octahedral sites will be an interstitial site. So you have both octahedral and tetrahedral sites. So octahedral, that means around 8 lattice atoms, you get one space in between this atom. That is an octahedral interstitial site. And if it is between 4 iron atoms, so somewhere here it will be. Then you have an tetrahedral sites. And carbon is always good in taking the octahedral sites because there is more space. For this transformation to occur from FCC to VCC, which happens at higher temperature, this happens very easily because temperature is high, energy is high, so diffusion takes place. But when we quench it, the carbon which is in the octahedral lattice has to rearrange in such a way, but it is not allowed. So what will happen is the carbon will go to this edge. Once it goes each edge, this system gets elongated. So that is what is represented here. So once it is elongated, this is an BCT crystal structure. That's the reason you have a martensite, which is a needle-like structure because of this particular thing. One more thing, BCT is brittle than your VCC structure. So it has very few slip planes. It's hard and brittle. So the complete transformation diagram for an iron carbon alloy of this one. So this is a diagram which is taken from Callister book for your reference. So A represent your austenite, P represent your pearlite, B is your bainite, and M is your martensite structure. So somewhere this red line as indicated before, this is 0%, where the initial transformation has to start. The green one is your 100% once it is completed, and the blue one is your 50%. So in between the blue and red, it is 25, and blue and green, it is 75. So if you are doing any transformation within this zone, you end up in pearlite. If you do anything between 550 to 200, you end up in bainite phase, and below that you end up in your martensitic phase. So we will superimpose some different cooling curves, which we already saw before as an explanation. So if you do different cooling curves, that 1, 2, 3, 4, 5, 6, 7 are there. So the distribution is understood. So when you do it 1, you end up in coarse pearlite. If you do 2, you end up in medium pearlite. So if you 3, again you end up in medium pearlite. If it is 4, you end up in fine pearlite. And if you do it 5, where the cooling curve is such a way that it's only 50%, and then you end up in also martensite plus your pearlite. So 50% is converted pearlite, and remaining 50% is converted into martensite. But if you are going below this critical cooling rate, you always end up in martensitic structure. Or if you do the transformation with respect to 8, then you end up in lower bainite structure. So these are the different cooling curves which are superimposed in your TTT diagram. So you can have your own also, nothing wrong with it. So this is one problem for you. So having them in mind, the diagram, this diagram, we are going to see how you can transform, what will be the end product if you do some particular transformation. So that is what this question is. So you're going to rapidly cool to 350, hold it for 10 power 4 seconds and quench it to room temperature. So have the diagram in hand and try to draw the line from 0th second. So immediately from 727, you quench it to 350 and hold it for 10 power 4 seconds. So what will be the end product? So if you take the next sample and from 727, quench it to 250 seconds within a second and hold it for 100 seconds, what will be the end phase you are getting? And third one, taking the sample from 727 degrees Celsius, quench it to 650 degrees Celsius. At 650, keep it only for 20 seconds. And from there, immediately take it and put it in 400 degrees Celsius and keep it for 10 power 3 seconds. And after that, immediately taking after 10 power 3 seconds, you are quenching it at room temperature. What will be the end microstructure you will get? So for the first one, so if you see, quenching it to 350 seconds. So this is your 350. So within 1 second or 0 second, you're putting at 350 and doing the transformation up to 10 power 4 up to this point. So straight line, 0 it crossed, 50 it is crossed, so 100 it is crossed. So 100% it is converted. We know around 350 you get your bainite structure. So that is what it's the end result, 100% bainite you end up. Now the second one we will see up to 250 and hold for 100 seconds. So 250, holding it for 100 seconds. 100 seconds is this point, you do up to this and then you quench it to room temperature. But thing is, it has never crossed the 0% line. So when it is not crossed anything, that means from here to here, it is only before the 0%. So you end up only in 100% martensite structure. The advantage of this one is if you directly quench from 727 to room temperature, lot of stress will be there. And if you do something like this, the stress in the material, which is generated by quenching will be least. So that is the advantage of this particular cooling system. And third one, we saw that it is a 3-step process. So we'll see that first at 650, keep it for 20 seconds. So this is the 20-second time. So that means 50% is getting converted. So at this point, you have 50% austenite and 50% Pierrelite. Then after 20 seconds, immediately cool to 400 seconds. This straight line indicates is only that this is a temperature drop for the second one. But the second transformation always again we have to start from the 0th second. So that's the reason it is a dotted line. So this is nothing. It's an only indication that the second transformation start from the 0th second for 400 degrees Celsius. From here again 0, it has been told that it has to be up to 10 power 3 seconds. So this is the 10 power 3. It has crossed the 0, 50 and 100. For sure, already 50% is got converted to Pierrelite. Only 50% is remaining. So that 50% is completely converted to bainite. Completely means because it is 100%. So the remaining 50% of austenite is 100% completed to bainite phase. So you end up in 50% Pierrelite and 50% bainite. So is it possible to have Pierrelite, bainite and martensite phase also? Yes, it is also possible. So if you take the same curve, first one I have, say if I want 50% Pierrelite, 25% bainite and 25% martensite. So it is possible. So with the first step, I got this one where I get 50% Pierrelite, so right. With the second one, okay, I go to 400, but I'm not going to keep it for 10 power 3 seconds, but I'm going to go up to this particular point. So this is going to be like 60 seconds. So this one 20 seconds, I keep at 650. Second one, I go to 400 and keep it for 60 seconds. That means initially 50% converted, remaining 50% of austenite. In that 50% is getting converted to bainite. And still remaining 50% of austenite is remaining, that is 25%. And from there you quench it to room temperature. So quench it to room temperature, you can directly draw a straight line. So then you end up at this point all like 25%, sorry, 50% Pierrelite, 25% bainite and 25% martensite. So that is also possible. Okay, I'll stop with that with time temperature. And next one is your continuous cooling transformation. I'll do this in next class for you. I hope you understood that time temperature transformation. Yes.
Yes, sir.
Okay, Ma. Thank you. That's for today's class. Those who have not uploaded your lab assessments,